The Earth's story, an environmental journey, imagine standing on a cliff, overlooking the ocean at dawn. The waves crash against ancient rocks below, the same rocks that have witnessed 4.5 billion years of Earth's history. This is where our story begins, not with charts and statistics, but with the living, breathing planet we call home. Today, we're going on a journey through time and space, exploring the remarkable story of Earth's environment. This isn't just a tale of problems and solutions, it's the story of the most complex system in the known universe. A planet that has reinvented itself countless times, and how one species, in the blink of an evolutionary eye, has become powerful enough to reshape it. By the end of our time together, you'll understand not just what's happening to our environment, but why it matters, how we got here, and what it means for the future. So settle in, and let's begin at the very beginning. Part 1. The living. Planet, the Goldilocks. Planet.Earth sits in what astronomers call the habitable zone, that perfect distance from the sun where water can exist in liquid form. But this isn't just luck. Our planet has spent billions of years fine-tuning itself into the perfect environment for life. Think of Earth as a giant self-regulating system. The atmosphere, the oceans, the land, and all living things work together in ways that seem almost miraculous. Scientists call this the Gaia hypothesis, named after the Greek goddess of Earth. While not every scientist agrees with all aspects of this theory, the basic idea holds true. Earth is more than just a rock with stuff living on it. It's an integrated system where life itself helps maintain the conditions for life. Consider the oxygen you're breathing right now. 21% of our atmosphere is oxygen, and nearly all of it was created by living organisms over billions of years. Early bacteria called cyanobacteria learned to photosynthesize, taking in carbon dioxide and releasing oxygen. This was actually a catastrophe at first, what scientists call the Great Oxidation Event, about 2.4 billion years ago. Oxygen was toxic to most life at the time, causing a mass extinction. But it also opened the door for complex life forms like us that could use oxygen for energy. The water cycle, Earth's circulatory system. Water is constantly moving on Earth, and this movement is essential to life. Every year, about 500,000 cubic kilometers of water evaporates from the oceans. This water vapor rises, cools, and forms clouds. These clouds travel over land, where they release rain and snow. This precipitation feeds rivers and lakes, waters plants, and eventually flows back to the ocean. But here's what makes it remarkable. This isn't just moving water around. The water cycle distributes heat around the planet, moderating temperatures. It erodes mountains, creating soil. It dissolves minerals and nutrients, making them available to plants and animals. Without the water cycle, Earth would be as dead as Mars. The water cycle also acts as a massive distillation system. When water evaporates from the ocean, it leaves salt and pollutants behind. This means rain is naturally pure water, a gift from the sky that has sustained life for eons. Of course, it can pick up pollutants as it falls or flows, but the cycle itself is a purification process. The carbon cycle. Life's chemical foundation. Carbon is the building block of life. And like water, it moves through Earth's systems in a complex cycle. Plants pull carbon dioxide from the air during photosynthesis, using sunlight to combine it with water to create sugars. Animals eat plants, using that stored energy and releasing carbon dioxide when they breathe. When plants and animals die, most of their carbon returns to the atmosphere through decomposition, but some gets buried in sediments. Over millions of years, heat and pressure can transform this buried organic matter into fossil fuels: coal, oil, and natural gas. This is important because it means fossil fuels are essentially ancient sunlight, stored chemical energy from plants that lived hundreds of millions of years ago. When we burn them, we're releasing carbon that was locked away for geological timescales, putting it back into the atmosphere and oceans far faster than natural processes can reabsorb it. The ocean plays a crucial role in the carbon cycle too. It absorbs about a quarter of the carbon dioxide humans emit each year. Tiny marine organisms use carbon to build shells and skeletons. When they die, they sink to the ocean floor, eventually forming limestone and other carbonate rocks. Over millions of years, this process has stored enormous amounts of carbon. The nitrogen cycle, the overlooked essential. While carbon gets most of the attention, nitrogen is equally vital. It makes up 78% of our atmosphere. But in this form, most living things can't use it. Nitrogen gas is two nitrogen atoms bonded so tightly together that they're essentially locked. Special bacteria, often living in the roots of plants like beans and clover, can break this bond and convert atmospheric nitrogen into ammonia, a form plants can use. This process, called nitrogen fixation, is one of the most important chemical reactions on Earth. Without it, plants couldn't grow, and life as we know it couldn't exist. Animals get their nitrogen by eating plants or other animals. When living things die and decompose, other bacteria convert nitrogen compounds back into atmospheric nitrogen, completing the cycle. Humans have learned to fix nitrogen industrially through the Haber-Bosch process, creating synthetic fertilizers that have helped feed billions. But this has also disrupted the nitrogen cycle, leading to environmental problems we'll explore later. Part 2. The changing climate. The greenhouse affect Earth's thermal blanket. Let's talk about something that's become politically charged but is actually straightforward physics, the greenhouse effect. Without it, Earth would be frozen, with an average temperature around 0 degrees Fahrenheit instead of the current 59 degrees. The greenhouse effect is what makes our planet habitable. Here's how it works. Sunlight passes through the atmosphere and warms Earth's surface. The surface then radiates this heat back towards space as infrared radiation. Certain gases in the atmosphere, particularly carbon dioxide, methane, and water vapor, absorb some of this infrared radiation and re-emit it in all directions, including back toward Earth. This trapped heat warms the planet. Think of it like a blanket. The blanket doesn't generate heat, but it slows the loss of your body heat, keeping you warm. Greenhouse gases are Earth's blanket. Problem isn't the greenhouse effect itself. The problem is that we're thickening the blanket. Since the Industrial Revolution, humans have increased atmospheric carbon dioxide from about 280 parts per million to over 420 parts per million. That's a 50% increase in just over 2 centuries. Evidence from ice cores, reading Earth's diary. How do we know what Earth's atmosphere was like hundreds of thousands of years ago? The answer lies frozen in ice. In places like Antarctica and Greenland, snow falls year after year, compressing the snow below into ice. As snow becomes ice, it traps tiny bubbles of air. These bubbles are time capsules, preserving samples of the ancient atmosphere. Scientists have drilled ice cores more than 2 miles deep, revealing atmospheric conditions going back 800,000 years. These cores show a clear relationship between carbon dioxide levels and temperature. When CO2 was high, Earth was warm. When it was low, ice ages gripped the planet. What's striking is how stable the climate was for the past 10,000 years. The period when human civilization developed, carbon dioxide levels hovered around 280 parts per million. Temperatures were stable. This stability allowed agriculture to flourish, and cities to grow in predictable locations. The ice cores also reveal something sobering: the current rate of CO2 increase is unprecedented in at least 800,000 years. Past changes happened over thousands of years. We've achieved a similar magnitude of change in decades. The ocean's hidden role. The ocean isn't just affected by climate change. It's one of the primary regulators of climate. Ocean currents act like a global conveyor belt, moving heat from the equator toward the poles. The Gulf Stream, for instance, carries warm water from the Caribbean to the North Atlantic, giving Western Europe a much milder climate than its latitude would suggest. The ocean also absorbs enormous amounts of heat. In fact, over 90% of the excess heat trapped by increased greenhouse gases has been absorbed by the ocean, not the atmosphere. This has slowed atmospheric warming, but has serious consequences for marine life and ocean chemistry. When carbon dioxide dissolves in seawater, it forms carbonic acid, lowering the ocean's pH. Since the Industrial Revolution, ocean pH has dropped by about 0.1 units, representing a 30% increase in acidity. This might not sound like much, but it's enough to interfere with the ability of corals, shellfish, and many other marine organisms to build their calcium carbonate structures. Imagine trying to build a sandcastle while someone keeps dissolving the sand. That's what ocean acidification does to shell-building organisms. Temperature. Rise what a few degrees really means when scientists say the global average temperature has risen by about 1.2 degrees Celsius since pre-industrial times. It's easy to think that's not much. On a hot day, a degree or two seems trivial, but this is the global average, including oceans, land, day, night, summer, and winter. To shift the entire planet's average temperature by even 1 degree requires an enormous amount of energy. It's the difference between an ice age and the climate that allowed civilization to flourish. Moreover, the warming isn't uniform. The Arctic is warming at more than twice the global average rate. Some regions experience more extreme changes than others. And it's not just about average temperatures, it's about the increase in extreme weather events. Think of climate like a bell curve. Most days are near average. With fewer extremely hot or cold days, as you shift the whole curve warmer, you not only increase average temperatures, you dramatically increase the frequency of extreme heat. Days that were once rare become common. Days that were impossible become possible. Feedback loops. The accelerator's climate change doesn't happen in a straight line. It triggers feedback loops that can accelerate warming. One major feedback involves ice and snow. Ice reflects about 90% of sunlight back into space. When ice melts, it exposes darker ocean water or land, which absorbs much more sunlight. This causes more warming, which melts more ice, which causes more warming. This feedback is why the Arctic is warming so rapidly. Another feedback involves permafrost, permanently frozen ground in Arctic regions. Permafrost stores enormous amounts of carbon in frozen plant material. As it thaws, microbes decompose this organic matter, releasing carbon dioxide and methane. This adds more greenhouse gases to the atmosphere, causing more warming, thawing more permafrost. There are also negative feedbacks that slow change. More CO2 can stimulate plant growth, removing CO2 from the atmosphere. Higher temperatures increase evaporation, creating more clouds, which can reflect sunlight. But scientists' best understanding is that positive feedbacks outweigh negative ones, meaning the climate system amplifies rather than dampens warming. Part 3, biodiversity. And ecosystems, the web of life. Imagine walking through a forest. You see trees, birds, maybe a deer, but beneath your feet and all around you is an invisible world of staggering complexity. The soil is alive with billions of bacteria, fungi, insects, and worms. The trees are connected by underground fungal networks that share nutrients and information. The birds control insect populations. The deer spread seeds. Every organism is connected to countless others. This is an ecosystem, and Earth is covered with them. Each unique and each essential. Tropical rainforests, coral reefs, grasslands, wetlands, tundra, each supports a different community of life adapted to its specific conditions. Here's what makes ecosystems remarkable: they're self-organizing and self-maintaining. A forest creates its own climate, cycling water and maintaining humidity. A coral reef builds its own structure. These systems have evolved over millions of years to be resilient and productive, but they're not infinitely resilient. Every ecosystem has a breaking point, and humans are testing those limits worldwide. The sixth mass extinction. Earth has experienced 5 mass extinctions in its history. Events where more than 75% of species disappeared. The most famous killed the dinosaurs 66 million years ago. Scientists increasingly believe we're in the 6th mass extinction. But this time, the cause isn't an asteroid or volcanic eruption. It's us. Current extinction rates are estimated to be 100 to 1,000 times higher than the natural background rate. We're losing species faster than we can even discover and name them. The World Wildlife Fund's Living Planet report shows an average 68% decline in vertebrate populations since 1970. Why does this matter beyond the sadness of losing beautiful creatures? Because ecosystems are like intricate machines with millions of interconnected parts. Remove enough parts, and the whole system can collapse. Bees pollinate crops. Forests produce oxygen and absorb carbon. Wetlands filter water and prevent flooding. When we lose species, we lose these services. There's also the precautionary principle. We don't fully understand how ecosystems work. Removing species is like pulling rivets out of an airplane wing. The plane might fly fine without a few rivets. But eventually, you pull one that matters, and the consequences are catastrophic. Deforestation erasing Earth's lungs. Forests cover about 30% of Earth's land surface, but we're cutting them down at an alarming rate. Every year, An area of forest about the size of Greece disappears, mostly in tropical regions. The Amazon rainforest, often called the lungs of the earth, illustrates what's at stake. This single ecosystem contains about 10% of all species on Earth. It generates its own rainfall through evapotranspiration. With trees releasing water vapor that forms clouds, it stores enormous amounts of carbon in its trees and soil. When forest is cleared, often by burning, that carbon returns to the atmosphere. Deforestation accounts for about 10% of global greenhouse gas emissions, but the damage goes beyond carbon. Clearing forests disrupts rainfall patterns. Sometimes far from the cleared area, it destroys habitat for countless species. It eliminates resources that indigenous peoples depend on. Once a certain threshold of clearing is reached, rainforests can tip into a drier state, becoming savanna. Scientists worry the Amazon is approaching this tipping point. If it crosses that threshold, it could trigger a rapid die-off of the remaining forest, releasing decades' worth of carbon emissions all at once. Ocean ecosystems under pressure. If forests are Earth's lungs, oceans are its heart. And that heart is under stress. Coral reefs, often called rainforests of the sea, are particularly vulnerable. These ecosystems support about a quarter of all marine species despite covering less than 1% of the ocean floor. Corals are animals that live in partnership with photosynthetic algae. The algae provide the coral with food through photosynthesis, and the coral provides the algae with a protected environment. It's a perfect partnership that has existed for millions of years. But this partnership is temperature sensitive. When water gets too warm, corals expel their algae in a stress response called bleaching. Without their algae, corals starve and turn white, like bone. If conditions improve quickly, corals can recover, but repeated or prolonged bleaching kills them. In recent years, mass bleaching events have become more frequent and severe. The Great Barrier Reef, the largest living structure on Earth, has experienced multiple mass bleaching events. Many coral reefs worldwide have already died or are severely degraded. The loss of coral reefs would be catastrophic. They protect coastlines from storms and erosion. They support fisheries that feed hundreds of millions of people. They generate billions in tourism revenue. And they're home to incredible biodiversity that we're only beginning to understand. The importance of soil here is something that doesn't get enough attention. Soil. It seems like just dirt. But healthy soil is one of Earth's most valuable resources. Soil takes centuries to form through the slow breakdown of rock, the accumulation of organic matter, and the work of countless organisms. A single tablespoon of healthy soil contains more organisms than there are people on Earth. These organisms break down organic matter, making nutrients available to plants. They improve soil structure, helping it hold water and resist erosion. But we're losing soil at an alarming rate. Intensive agriculture, deforestation, and development cause erosion that strips away topsoil faster than it can form. It's estimated that we're losing 30 soccer fields worth of soil every minute worldwide. At current rates, some estimates suggest we have only 60 years of topsoil left for farming. Without healthy soil, we can't grow food. Without soil to hold water, floods and droughts become more severe. Without soil organic matter, we lose a significant carbon sink. Soil might not be glamorous, but it's literally the foundation of terrestrial life. Part 4, Human Impact. And pollution. The plastic age. Archaeologists divide human history into ages based on the dominant material technology: the Stone Age, Bronze Age, Iron Age. Future archaeologists, if any exist, might call our era the Plastic Age. Plastic is a miracle material in many ways. It's cheap, durable, versatile, and lightweight. These properties have made it ubiquitous, but they're also why it's become an environmental disaster. Since the 1950s, we've produced over 9 billion tons of plastic, and most of it still exists, somewhere. Plastic doesn't biodegrade in any meaningful time frame. It photodegrades, breaking down into smaller and smaller pieces called microplastics. These tiny particles are now everywhere in the deepest ocean trenches, at the top of Mount Everest, in Arctic snow, in the rain, in the food we eat, in our bodies. Studies have found microplastics in human blood, lungs, and placentas. We don't yet fully understand the health impacts, But we do know that many plastics contain or absorb toxic chemicals. Fish mistake plastic particles for food, filling their stomachs with indigestible material. Seabirds feed plastic to their chicks. Whales have been found dead with stomachs full of plastic bags. The Great Pacific Garbage Patch, a concentration of plastic debris in the North Pacific, is often imagined as a solid island of trash. The reality is more insidious. It's a vast area where plastic particles outnumber plankton. This disrupts the base of the ocean food web in ways we're only beginning to understand. Air pollution, the invisible killer every breath we take, should be life-giving. But for much of humanity, it's also hazardous. Air pollution kills an estimated 7 million people annually, more than war, malaria, and HIV combined. The problem varies by location. In many developing countries, the primary issue is indoor air pollution from cooking fires using wood or dung in poorly ventilated spaces. In cities worldwide, vehicle emissions and industrial activity create smog, a toxic mixture of particles and gases, fine particulate matter. Particles smaller than 2.5 micrometers are particularly dangerous. They're small enough to penetrate deep into lungs and even enter the bloodstream. Long-term exposure increases the risk of heart disease, stroke, lung cancer, and respiratory diseases. But air pollution isn't just a health issue. Many air pollutants are also greenhouse gases or produce them. Black carbon from incomplete combustion settles on snow and ice, darkening it and accelerating melting. Air pollution can alter rainfall patterns and damage ecosystems. There's good news, though. Air quality has improved dramatically in many wealthy countries through regulations like the Clean Air Act in the United States. Cities like Los Angeles, once synonymous with smog, now have much cleaner air. This proves that with political will and proper regulation, air pollution can be addressed even while maintaining economic prosperity. Water pollution. Poisoning, the source of life water, is essential for all life. Yet we treat water bodies like waste disposal systems. Rivers, lakes, and oceans receive agricultural runoff carrying fertilizers and pesticides, industrial discharge containing heavy metals and toxic chemicals, and sewage from cities. Agricultural runoff creates particular problems. Fertilizers containing nitrogen and phosphorus promote excessive algae growth. When this algae dies and decomposes, it consumes oxygen in the water, creating dead zones where fish and other organisms can't survive. The Gulf of Mexico has a dead zone the size of New Jersey that forms every summer. Industrial pollution has contaminated water supplies, with everything from mercury to forever chemicals called PFAS. These substances persist in the environment and accumulate in organisms, reaching toxic levels in predators at the top of food chains, including humans. Even pharmaceuticals are showing up in waterways. Birth control hormones in wastewater can feminize fish. Antibiotics promote the development of resistant bacteria. Access to clean water is already a crisis for billions of people. The World Health Organization estimates that over 2 billion people lack safely managed drinking water. Climate change and pollution are making this worse, creating a situation where water, the most abundant substance on Earth's surface, becomes a scarce resource for human use. Chemical contamination, the legacy we're leaving. Since World War II, the chemical industry has produced tens of thousands of synthetic chemicals. These substances have brought enormous benefits: medicines that save lives, materials that enable modern technology, pesticides that increase crop yields. But many of these chemicals persist in the environment and accumulate in living tissues. DDT, banned in many countries decades ago, is still found in organisms worldwide. PCBs, also banned, still contaminate sediments and organisms. New chemicals are constantly being introduced, often without adequate testing of their long-term environmental and health effects. The PFAS family of chemicals, called forever chemicals because they don't break down, illustrates the problem. They're used in everything from nonstick pans to firefighting foam to water-resistant clothing. Now they're found in the blood of almost every person tested. They've been linked to various health problems, including cancer and immune system dysfunction. We've essentially turned Earth into a massive, uncontrolled chemistry experiment. Every organism alive today, from polar bears to penguins to people, carries industrial chemicals in their tissues that didn't exist in nature a century ago. Part 5, Solutions and Hope. Renewable Energy. Powering the Future. The story of renewable energy over the past decade has been remarkable. Solar and wind power have gone from expensive alternatives to the cheapest sources of new electricity generation in most places. This wasn't inevitable, it happened because of sustained investment, technological innovation, and supportive policies. Solar panel costs have dropped by about 90% since 2010. Wind turbine efficiency has improved dramatically. Battery costs have fallen by about 85%, making electric vehicles competitive with traditional cars and enabling grid storage of renewable energy. The transition to renewables isn't just about fighting climate change. It's about energy security, not depending on finite resources controlled by a few countries. It's about air quality, as renewable energy produces no air pollution. It's about economics, creating jobs and industries. Countries like Denmark generate over half their electricity from wind. Iceland uses geothermal and hydroelectric power for nearly all its energy needs. Costa Rica often runs on 100% renewable electricity for extended periods. These examples show it's technically possible. The question is political will and investment. Regenerative agriculture, healing the land modern. Industrial agriculture has fed billions, but at a cost: eroded soil, depleted aquifers, pollution from fertilizers and pesticides, and significant greenhouse gas emissions. But there's a better way, one that works with natural systems instead of against them. Regenerative agriculture encompasses various practices minimizing soil disturbance, keeping soil covered with plants or mulch, maximizing plant diversity, integrating livestock, and avoiding synthetic inputs when possible. These practices build soil health, increase biodiversity, improve water retention, and capture carbon from the atmosphere. Farmers. Practicing regenerative agriculture report reduced input costs, more resilient crops, and often higher profits. The food produced can be more nutritious, with higher levels of vitamins and minerals that come from healthy soil. Scaling these practices could transform agriculture from a major source of environmental problems into a climate solution. Some estimates suggest that regenerative agriculture on a global scale could sequester enough carbon to offset a significant portion of annual emissions while improving food security and farmer livelihoods. Protecting and restoring nature. Sometimes the best solution is the simplest: protect what remains and help damaged ecosystems recover. Conservation efforts have saved species from extinction and preserved ecosystems. The creation of national parks and protected areas has safeguarded some of Earth's most important habitats. But protection alone isn't enough. We also need restoration. The good news is that nature is remarkably resilient when given a chance. Reforestation projects are planting billions of trees. Coral restoration programs are cultivating heat-resistant corals. Rivers that were once declared dead have been cleaned up and now support life again, large-scale. Restoration projects show what's possible. China's Loess Plateau Restoration Project transformed a degraded landscape larger than Belgium into productive farmland and forest, lifting millions out of poverty while capturing carbon and controlling erosion. Costa Rica reversed decades of deforestation, and now forest cover is expanding. These successes demonstrate that environmental restoration isn't just possible, it's practical and beneficial. Every restored forest, wetland, and reef provides services worth far more than the cost of restoration. Circular economy, rethinking waste. Our current economy is linear: extract resources, make products, use them, throw them away. This model is fundamentally unsustainable on a finite planet. The alternative is a circular economy where materials are reused, repaired, and recycled, and waste is designed out of the system. Some companies are already moving this direction. Interface. A carpet manufacturer has committed to using only recycled and bio-based materials. Patagonia repairs and resells used clothing. Some electronics companies are designing products to be easily disassembled and recycled. The circular economy isn't just about recycling. It's about fundamentally rethinking how we design and use products. It means designing for durability and repairability instead of planned obsolescence. It means sharing and renting instead of owning. It means turning one industry's waste into another's raw material. The economic opportunity is enormous. One study estimated that a circular economy could generate trillions in economic benefits while dramatically reducing environmental impact. It creates jobs in repair, remanufacturing, and recycling. It reduces dependence on resource extraction, individual action. Your role in the story, it's easy too. feel helpless in the face of global environmental challenges. What difference can one person make? But collective individual action, combined with systemic change, is essential. Your choices matter. Energy use, transportation, diet, consumption will have environmental impacts. Reducing meat consumption, particularly beef, significantly reduces your carbon and water footprint. Flying less, or not at all, eliminates a major source of emissions for many people. Buying less stuff and buying quality items. That last reduces waste and resource extraction. But individual action isn't just about reducing harm. It's about supporting solutions, installing solar panels, buying electric vehicles, supporting businesses with sustainable practices, investing in green funds. These choices send market signals and help scale solutions. Perhaps most importantly, individuals can demand systemic change, vote for politicians who take environmental issues seriously, support environmental organizations, speak up in your community, talk to friends and family. Culture changes when enough individuals change their minds and behaviors. The environmental movement has achieved enormous successes through collective action, the Montreal Protocol, that healed the ozone hole, the Clean Air and Clean Water Acts, the creation of protected areas worldwide. These didn't happen automatically. They happened because people demanded them. Technology and innovation reasons for hope. Human ingenuity has created many of our environmental problems, but it's also creating solutions. Beyond renewable energy, numerous technological innovations offer hope. Carbon capture technology that removes CO2 from the air or from industrial emissions is improving, while not a substitute for reducing emissions. It could help address legacy emissions. Lab-grown meat could provide the benefits of meat without the environmental cost of livestock. Vertical farming could produce food in cities, reducing transportation emissions and land use. New materials could replace plastics with biodegradable alternatives. Some innovations are surprisingly low-tech. Simple clay pot irrigation can drastically reduce water use in farming. Traditional building techniques using local materials can create comfortable buildings without energy-intensive heating and cooling. The key is that we don't have to invent entirely new solutions from scratch. Many solutions already exist. They just need to be scaled up and implemented widely. The technology to transition to renewable energy exists. The knowledge to practice regenerative agriculture exists. The challenge is deployment, not invention. The path forward, a story still being written. We've journeyed through billions of years of Earth history, explored the planet's major systems, examined the unprecedented human impact on those systems, and looked at solutions that offer hope. So where does this leave us? The reality is sobering. We're in the midst of rapid environmental change driven by human activity. The challenges are real, significant, and urgent. If we continue on the current path, the consequences will be severe, more extreme weather, ecosystem collapse, mass extinction, resource scarcity, human displacement, and suffering. But the future isn't predetermined. Unlike past mass extinctions or climate changes, this one is driven by human choices, which means different choices can lead to different outcomes. We have the knowledge and increasingly the technology to address these challenges. What we need is the collective will to act. The story of Earth's environment is still being written. We're living in a critical chapter, where decisions made in the coming years will reverberate for millennia. Will we be remembered as the generation that continued business as usual even as the warning signs flashed red? Or will we be remembered as the generation that changed course, that chose a sustainable path, that preserved Earth's incredible biodiversity and beauty for future generations? Every great story features a moment where the protagonist must choose between the easy path and the right path. We're at that moment now. The easy path is continuing as we are, hoping someone else will solve the problems. The right path requires change, sacrifice, and work, but it leads to a future worth living in. You're part of this story. Your choices, your voice, your actions matter, not just for distant future generations or polar bears or coral reefs, though they matter too. Your choices matter for you, for your community, for the world you live in right now. As we close this journey, remember that rocky cliff we started on, overlooking the ocean. Those ancient rocks have witnessed ice ages and warm periods, mass extinctions and evolutionary explosions, the rise and fall of countless species. Through it all, Earth has endured, changing but persisting. We're not trying to save the planet in some ultimate sense. Earth will continue long after we're gone. What we're trying to save is the particular configuration of Earth's systems that makes human civilization possible. We're trying to preserve the incredible diversity of life that shares this planet with us. We're trying to pass on to our children and grandchildren a world at least as beautiful, as abundant, and as full of possibility as the one we inherited. That's a story worth telling. More importantly, it's a story worth living. The ending hasn't been written yet. Let's make it a good one.